Swayam Prabha. Digital India. Educated India.
Friends, welcome to the 35th lecture on the course on Advanced Steel Design. In this course, we are going to learn more about checking the stability of cylindrical shells. Okay, or tubes, let us say, okay, tubular elements. Now, the stiffened cylinders are one of the major structural components of special kind of structures. They are very common in offshore compliance structures. So, we are now talking about stiffened cylinders. They are very common structural members in offshore structures. They can be classified as ring stiffened, stringer stiffened, and ring stringer stiffened. Cylinders. Okay. So, the whole batch is also called as orthogonally stiffened cylinders. They are also known as orthogonally stiffened cylinders. Now, let us quickly understand what are stringers. Stringers are longitudinal stiffeners. Which are either attached externally or internally to the cylinder at equal spacing. These stiffeners can be of cross section. There can be a flat bar, there can be angles, there can be T sections and so on. They are generally integrally welded to the shell and they help in resisting the lateral loads. Now, the structure is fabricated from hot or cold formed plates. Essentially, the welding will be a butt welding, and therefore, we need to check whether the stiffened cylinders are stable for a given configuration. Okay? The geometric distortion and residual stresses are some of the common problems which you have heard in steel structures which commonly occur under welding process. So, we can say that welding process initiates geometric distortion and residual stresses. So, upon the types of failure, orthogonally stiffened cylinders generally fail by buckling. Okay. This buckling can be in different modes. They can be shell buckling, panel stiffener buckling, panel ring buckling, and column buckling. Okay. Now, let us try to draw them and show how do they look like. Let us say this is my cylinder. Okay. Now, when there are different layers along the length and along the circumference, some of them will have solid concentrations of stresses, some of them will have negative. I am showing the positive ones as firm lines, stress concentration factors, and the negative ones as dotted lines. So, this form of failure is called shell buckling. Okay. They generally form a pair, they generally occur alternatively. They generally occur alternatively. Okay. The second one is called panel stiffener buckling. Let us take a shell again, cylinder. Now, what happens in this case is the panels will start buckling. So, I should say and again there will be on different layers the compression and tension. So, this is panel stiffener buckling. Panel rim buckling is a different phenomena which occurs in this form. Again there will be alternate tension and compression, inundation and solid bulging. So, this will be panel ring buckling. Of course, general buckling looks like this. So, there will be tension and compression stress concentrations all along the length of the member. So, this is called general buckling. Whereas, the column buckling phenomena will be similar to what we have seen in a column. So, these are different buckling modes of failure of orthogonally stiffened cylinders. We will do a problem in relationship with an international code and try to understand how code classifies stability, okay, of these set of cylinders. So, we will do a simple exercise. We will say check the stability of a ring stiffened circular cylinder under axial compressive stress of 30 Newton per mm square against shell buckling. We will just look only for one mode of failure. So, the data given is like this. The diameter of the cylinder is 5 meters, thickness of the cylinder (30 millimeters), length of the cylinder 8 meters, spacing of the ring stiffeners is 800 mm center to center, and take sigma y as 433 Newton per mm square. Okay, let us do this. So, let us say the solution. First, let us try to find out the stability requirements. So, we will use DNV recommended practice C202 code. Okay. So, according to section 3.1 of the code, in the moment I say code, we are referring to this, okay, of the code. The stability requirements of a circular cylinder under axial stress is given by the following equation: sigma d should be less than or equal to f of ksd. We will call this equation number 1, where sigma d is known as design shell buckling strength, okay, where f ksd is called characteristic buckling strength. This is given by Fks by gamma m, where Fks is actually the characteristic buckling strength, okay, not Ksd. Okay. So, now the question is, how do you find Fks? Let us go for characteristic buckling strength. Fks. So, we know Fks is given by Fy by root of 1 plus lambda 4, we call equation number 2, where lambda square is given by Fy by sigma d of sigma AO by F EA plus sigma MO by F EM plus sigma HO by F EH plus tau naught by F E tau. Equation number 3. And sigma D, the design strength, is governed by the square root of squares of sigma A plus sigma M square minus sigma A plus sigma M of sigma H plus sigma H square plus 3 tau square. We call equation number 4. They are available in DNV RPC 2002 code. Let us substitute the values. We know the design axial stress which is applied on the problem, sigma A is 30, which is given in the problem. Okay. And the design bending stress, sigma M, we should take it as 0 because we are saying it is under pure axial stress. So, then the design circumferential hoop stress, sigma H, is also 0 in our problem. The design shear stress, tau, is also set to 0. Now, I substitute this in equation 4, okay, by substituting in equation 4, we get sigma D as 30 megapascal. The characteristic buckling strength of circular cylinder under shell buckling is given by this following equation. Of circular cylinder for check under shell buckling is given by section 3.4.2 of page 15 of the code. I am producing the equation again here. Fe is given by C times of pi square E by 12 1 minus nu square of square T by L the whole square. We will call this equation number 5. Whereas, in the above equation, C is called reduced buckling coefficient. Is given by psi times of root of 1 plus rho epsilon by psi, the whole square. Okay. So, equation number 6. Now, what we do? We use table 3.2 of the code and we say psi is unity and zeta is 0.702 ZL, where ZL is L square by RT root of 1 minus mu square. We call this equation number 7A, this as equation number 7B, and this further, okay, this as 7B, and rho is given by 0.5 times of 1 plus R by 150 T. This is R, okay, whereas this is nu minus 0.5. We call this 7C. Okay. Now we know the spacing, the stiffener. The spacing of the stiffener given is L, which is 800 mm. Okay. We also know the cylinder radius, which is R, is 2500 mm. We also know the cylinder thickness, which is T, is 30 mm. We also know the Poisson's ratio, which is nu, which is 0.3. Now substituting this in equation 7, we get ZL as 7.765, zeta as 5.451 and rho as 0.401. Now from equation 6, let us say equation 6, we get now the reduced strength, is it not? Equation 6 gives me the reduced buckling coefficient, is given by 2.404. You can see here in this equation, we have know all the values, you can substitute and get C. Now, the characteristic buckling strength is given by Fe, which is equal to C times of pi square E 12 1 minus nu square of square T by L the whole square. Is it not? That is the equation we have. Let us substitute 2.404 pi square 2.110 power 5, we are talking about steel, okay, 12, 1 minus, we have taken this as 0.3, the Poisson ratio, so 1 minus 0.3 square of square T by L the whole square. Am I right? So this value comes to about 641.64 Newton per mm square. So now let us check for the stability. From equation 3, what is equation 3? Let us see this equation here. From equation 3, we know this value can be now obtained for substitution. From equation 3, lambda bar square is given by Fy by sigma d times of sigma AO by FEA, right? Remaining all are said to be zeros, and not, which is coming to be 0.675. Substituting this in equation 2, what is equation 2? See here, equation 2 is giving you the characteristic buckling strength, okay, Ks. Fks is given by Fy by root of 1 plus lambda 4, right? Okay, so let us do that, which is going to be 297.514 Newton per mm square. So now, using section 3.1, page 13 of the code, okay, we get gamma m as 0.85 plus 0.60 lambda bar if lambda bar is between 0.5 and 10. Our lambda bar is 0.675. Therefore, we get gamma m as 1.343. Okay. Once we get gamma m, I can now find f ksd, which is nothing but f ks by gamma m, which is going to be 297.514 by 1.343, is it not, which is going to be 221.54 Newton per mm square. Now, since the design strength is 30, which is much lesser than FKSD, we can come to a conclusion that the circular cylinder is safe against shell buckling. Okay. Let us do one more exercise. We will say calculate the characteristic buckling strength of the stiffened cylindrical shell with the following data. Let us see what are the data given. So, diameter of the shell is 10 meters, thickness of the shell is 40 millimeters. Let us say we are using stiffeners as follows. We are using a flat bar of size 300 by 40 mm as stiffener. Ring frame spacing is 600 mm, center to center. Let us say the axial compressive stress is 40 megapascal and circumferential compressive stress is 70.4. Is 70 megapascal and yield strength of the material is 433. Okay. Let us solve this problem. So, 1. Let us find the characteristic buckling strength. I am using the same code, rather the same class. Okay. Fks is given by Fy by root of 1 plus lambda 4, we call C equation number 10, and we know lambda bar square is given by Fy by sigma d of sigma AO by Fe sigma plus sigma MO by Fem plus sigma HO by FEH plus tau naught by Fe tau. Equation 11, we already wrote this equation from the code, and we also know sigma d is given by square root of sigma A plus sigma m the whole square minus A plus m into sigma h plus sigma h square plus 3 tau square. Equation number 12. We know the design axial stress sigma A is minus 40 because it is compressive. Design bending stress sigma m is 0. Okay. Further, design circumferential stress is sigma h minus 70. Okay. And design shear stress tau is 0. Substituting in the above equation, we will get sigma d as 60.828 Newton per mm square. Okay. Let us now compute the elastic buckling strength. So, we use section 3.3.2 on page 14 of the code. Okay. Let us talk about the aspect ratio L by S. Let us see what is the value, where L is the distance or the spacing of the ring stiffeners, which is in this case 1000 mm. Now, distance between the longitudinal stiffeners we call this as S, which is 600 mm. So, the aspect ratio in our case is 1000 by 600, which is 1.667, which is greater than 1. When it is greater than 1, then the characteristic buckling strength of the cylindrical check for shell buckling is given by Fe is C times of pi square E by 12 1 minus nu square square T by L the whole square. We will call equation number 13. Now, the reduced coefficient C, reduced buckling coefficient C is given by psi times of square root of 1 plus rho epsilon by psi the whole square, equation 14. So, from table 3.2 of the code, psi is 4. So, zeta will be 0.702 Zs. Zs is S square by RT of root of 1 minus gamma square or nu square. Rho is 0.5 square root 1 plus R by 150 T minus 0.5. We call equation number 15. So, now we already know the spacing between the lateral stiffeners. S is 600 mm, cylinder radius R is 5000 mm, cylinder thickness T as 40 mm, and Poisson's ratio nu is 0.3. So, substituting these values, we get ZL as 1.638, zeta as 1.15 and rho as 0.369. So, substituting in equation 14, we get, that is equation 14. This is equation 14. Okay, we get C as 4.022. Therefore, the characteristic buckling strength is given by FEA under axial is C times of pi square E by 12 1 minus nu square square T by L the whole square. So, which will become 4.022 times of pi square 2.1 10 power 5 12 1 minus 0.3 square of square 40 by 600 the whole square, which now becomes 3392.78. Now, the elastic buckling strength under circumferential stress is given by values from table 3.2. So, we say psi is 1 plus S by L the whole square okay, and okay, we call this equation number 60A. Zeta is 1.04 S by L root ZS, okay, and ZL is S square by RT root of 1 minus nu square. Now, we know Z rho is 0.6, S, which is the distance between the longitudinal stiffness, is 600 mm, cylinder radius is 5000 millimeters, Poisson's cylinder thickness is 40 mm, Poisson's ratio is 0.3. So, substituting in equation 14, we get psi as 1.85. Equation 14 is what we have here, okay. Oh, equation 16, sorry, equation 16A, psi as 1.85 and zeta as 0.799. And these are all equation 16B, 16C and so on. Okay. So, now substituting this in equation 12, let us go back to this and try to find out capital C as 1.911. Equation 12 is what C for C here, oh, not equation 12, equation 14, sorry, equation 14. So, therefore, the characteristic buckling strength is given by FEH C times of pi square E by 12 1 minus nu square square T by L the whole square, which will be 1.911 pi square 2.110 power 5 12 1 minus 0.3 square square 40 by 600 the whole square, which becomes 1612.04 Newton per unit square. Now friends, lambda bar square is given by Fy by sigma d. See this equation? Equation 11, okay. So, substituting in equation 11, Fy by d sigma AO by FEA plus sigma HO by FEH, which is 0.393, and therefore, lambda bar will be 0.627. Okay. Hence, the characteristic buckling strength is given by Fks, which is Fy by root of 1 plus lambda 4, which is 402.996 megapascal. So, friends, in this lecture, we learnt an example, in fact, of finding the buckling strength of stiffened cylinder. In fact, we have used an international code and checked the stability as recommended by the code. Okay. So, that is the procedure how buckling strength or buckling stress estimates are practiced and applied in design as far as international codes are concerned. So, friends, in these set of lectures on stability, we learned different types of stability. We learned stability is a mode of failure, and we have learned the difference between stability and buckling, and we have derived the stability functions for axial compression, zero axial load and axial tension, the rotational and translational functions of stability equations from the first principles, and we really understood that the stiffness matrix formulated for a stability problem is more or less similar to that of a matrix generated for a simple analysis of statically indeterminate structure, provided we remember the order of the label and remember the stiffness matrix. Once you have this matrix, we have formulated the characteristic equation where we set KUU determinant to 0 for a non-trivial solution, and we obtained the characteristic equation. We used either stability charts or stability tables available in the literature to choose the psi value, the phi value, which is the ratio between the axial force and the Euler's critical load. And we found out that to satisfy this equation, and we determined this value. We also exposed to you the MATLAB programs useful to plot the stability functions and also subroutines to solve the problems to estimate the critical buckling loads. Okay. In the next lectures, we will talk about unsymmetric bending, curved beams and crane hook design and analysis using standard equations and MATLAB applications. Thank you very much and have a good day.